Hello. We will begin by seeing some inductive type definitions. These are commonly used to define data structures in computer science. So here I define the type of binary trees that hold data of a type A. So binary tree of type A can be constructed as either an empty tree or a fork of a left subtree, which is a binary tree, a piece of data at the node, which we call X, and a right subtree of the same type. Once we have this inductive definition, we can construct binary trees by using these two constructors. So here I construct a tree where the left subtree is empty, the root node contains data 2, and the right subtree is recursively a binary tree where the root contains 3, the left is empty, and the right subtree is a single node that contains 4. Similarly, we can inductively define propositions. So here I define the proposition XOR of two propositions P and Q. So XOR PQ itself is a proposition, and there are two ways to prove XOR PQ. The first one I call yes no, where you can supply a proof of P and a proof of negation Q in order to prove XOR PQ. Or the second way to construct a proof of XOR PQ, which I will call no yes, is to supply a proof of negation P and a proof of Q to obtain a proof of XOR PQ. Once we have these definitions, we can use XOR like we use any other propositional connective like and or. So let us prove this example, which is that 0 is equal to 0 XOR 0 is equal to 1. So we enter the tactic mode, observe the goal, and notice that this XOR is true due to the constructor yes no. So the left hand side is true and the right hand side is false. Notice Lean gives us the labels yes and no, which were given by us in the definition of XOR. We will prove these cases individually. To prove the case yes, we can use the decide tactic, and to prove the case no, we can again use the decide tactic, since these do not involve any variables. Observe that the labels XOR.yes, no, yes and no were completely specified by us and not built into Lean. That is, we can teach Lean about new propositional connectives. Let us define two propositions for the game NIM on two heaps. So these propositions will be mutually recursive. So the proposition Alice and M for each pair of natural numbers n m should hold if Alice has a winning strategy for the game nm. So there are two ways for Alice to win such games. We will call them first and second. Similarly, we have the proposition Bob nm indexed by natural numbers n and m, and there is only one way for Bob to win an nm game, which we call intro. Observe that the structure of the definition is exactly the same as that of a binary tree or XOR. So the first way for Alice to win is to pick a natural number k in between 1 and n, and then to show that Bob can win the game n minus k m. This is because after the first move, Alice becomes the second player, which we call Bob, in the remaining game n minus k m. Similarly, Alice can win if she can pick a natural number k in between 1 and m such that Bob can win the remaining game. And by Bob, we mean the second player after the first move, which is Alice in the original game. So how can Bob win this game? Notice that for Bob to win this game, we must have a strategy to counter whatever the first move made by Alice. That is, Bob must provide two functions left and right. So the left function is the strategy to follow if Alice plays on the first heap in the first move. So we need to map any natural number k in between 1 and n into a winning strategy for the first player in the game n minus km. Similarly, if Alice plays on the second heap in the first move, then no matter how many number of coins she picks from the second heap, Bob should be able to counter or win the remaining game, which we call n m minus k. This corresponds to the natural there exists for all definition for winning strategies of two-player games. Let us prove that Bob wins the game 0-0. We enter tactic mode. There is only one way to prove Bob 0-0, which is to apply bob.inrow. Once we apply bob.inrow, we get cases left and right as specified in the above inductive definition of Bob. Now we solve case left. We introduce k and hk, and we have to prove Alice 0 minus k 0. But notice that we already have a contradiction in the hypothesis, so we can apply omega to finish the proof. Similarly, in the right case, we have a contradiction, so we can apply omega again, and that proves that Bob wins the game 0-0. Let us prove a more interesting theorem for Alice. So we will prove that Alice wins the game 1-0. We can apply Alice dot first because Alice wins this game by playing on the first heap. We have to provide k, the number of coins to pick. We have to prove that k satisfies the constraints. So our k will be exactly 1. K satisfies the constraints trivially by deciding it. And we have to prove that Bob wins the game 0-0, which we have already proved. And we called the proof Bob 0-0. We will now prove that Alice also wins the 0-1 game, but we will prove this in term style. So we apply the constructor alice.snd with the value 1 for k. We use the decide tactic to show that k satisfies the constraints, and bob00 is given as the proof. Notice that these two proofs are the same proof. It is just that we are writing one in tactic mode and the other in term mode. We will define the function square from natural numbers to natural numbers in tactic mode. We introduce n, which is the argument of the function, and we say we have to return exactly n times n. If we evaluate square on 13, observe that we get the required output 169. This is the square function that we wrote earlier in term mode, but now I have written it in tactic mode. Let us prove a general theorem about the two-player nim game. For all n, Bob wins the game n. So here we have a for all quantifier in the goal. The proof of a for all quantified predicate is a function that maps any natural number n into a proof that Bob wins the game n. So we can use intro tactic to introduce the variable n, that is for all quantified, into the hypothesis. In written mathematics we write this as let n be any natural number. That is what intro n here corresponds to. Then we apply strong induction on n to split into two cases. In the case 0 we have to prove Bob 00, which we already have written. In the inductive case, observe that we have to prove a for all quantified statement. So we introduce this n into the hypothesis. Notice that this n shadows the earlier n, which is no longer required. We have to introduce the left hand side of this implication into the hypothesis. So this left hand side is nothing but the strong induction hypothesis for n. Observe it says for all m's, that is at most n, Bob wins mm. And we have to prove this for n plus 1. We proceed by applying bob.intro, and now we have to prove the left and right cases. In the left case, we can introduce the variable k and the hypothesis on k, and we have to prove that Alice wins the game n plus 1 minus k n plus 1. Alice wins this by picking k coins from the second pile. So we apply alice.snd with the value k, and now we have to solve the cases hk and smaller. Case hk is easy, it is already in the hypothesis under the name hk, so we use exact hk. Notice that the two hk's here are distinct. The hk in case hk is just a label that we gave in the inductive definition of Alice, and the hk in the exact hk is the name we gave for the hypothesis. Now we have to prove that Bob wins the game n plus 1 minus k n plus 1 minus k. So we want to apply the strong inductive hypothesis for n. We just need to prove that n plus 1 minus k n plus 1 minus k is less than or equal to n. Since k is greater than or equal to 1 is already in the hypothesis, omega can find this for us. So we say this proof literally reads Apply the strong induction hypothesis on n plus 1 minus k by concluding that n plus 1 minus k is less than or equal to n using 1 less than or equal to k in the hypothesis. The proof of the right case is very similar, so we can copy and paste the left case to prove the right case. The only change we have to make is that Alice place on the first pile. That finishes the proof of this theorem. Thank you for watching. Bye.